Hello, hello. This week's Fiddler is a variation on a fairly well-known logic puzzle about comparisons. And it reminds me a lot of, there are a lot of these comparison puzzles out there. I think the most famous one is the one about the counterfeit coin, where you have, I think it's 10 coins, one of which is counterfeit, that weighs either more or less than the other coins, and you have to determine which one's counterfeit in three weighings, something like that. So this is a similar problem. And the problem that we have here is that I have 25 sprinters, and I want to find the fastest, the second fastest, and the third fastest of these sprinters. And the only way that I can sort them is by running races. And so in any particular race, I can run 10 at a time. And the question is, how many races do I need to run, right? So the idea being, I can figure out the order of 10 at a time, but to compare across races, I don't have a stopwatch or anything, so I can't compare them across races. I need to actually race them against each other if I want to know whether one person is faster than another, or use this transitive property where if A is faster than B and B is faster than C, then I know that A is faster than C as well. And this is a variation of another puzzle, a fairly well-known puzzle that I think it was a Google interview question for a while, and so that's why it became famous, perhaps. Where it's essentially an equivalent question, except you can only run 5 at a time instead of 10 at a time. I actually like this 10 at a time better than 5 at a time. I think the reframing is really nice. So anyway, you'll see what I mean in a second. So how many races do I need to run? So right away, I think it's fairly obvious that you could do this in 4 races, right? You could race, the first 10, the second 10, the third 5, right? And then you could just race the top 3 of those 3 races, and that would very easily get you an ordering and get you the top 3 overall. And also fairly obviously can't be done in 2, right? Because in 2 races, you can only race 20 people, and that leaves 5 people that haven't raced at all. And there's no way you could possibly determine whether or not they were in the top 3. So the only real question here is, can this be done in 3 races? And so, you can pause here and try to think about if you want, but I'm going to try to give you a helpful reframing for this question to maybe think about it. So the first thing to note here is that the first and third races here really have no decision making in them at all, right? And what do I mean by that? Well, if you think about the first race, I'm just picking 10. It really doesn't matter which 10 I pick. I'll call them the first 10, but there's no difference between which 10 I pick in the first race. It's a completely arbitrary selection. And when we get to the third race, assuming we're trying to do it in 3, in the third race, I have to pick everyone that's left that could possibly be in the top 3. And so the only real choice that I have here is who gets to race in the second race. And another way to reframe that is, which, if any, of the racers from the first heat do I include in the second heat, so that when I get to the third heat, I can sort the top 3 and figure out who the top 3 are. So, the reason I reframe it like this is, again, in the second heat, I might pick nobody from the first heat, but I might pick some from the first heat, and everyone else hasn't raced before. They're all equivalent. So this is really the only decision I have to make, is which racers from the first heat do I pick in the second. So I think that's a useful reframing. So if you haven't solved the puzzle yet, go ahead and pause and think about it. But I will fairly quickly walk through a solution here. I'm fairly sure it's the only one. And that solution is to just take the second place from the first heat only. They're the only ones you want to race in the second heat, and then you race them with 9 new racers. So why does this work? So after the second heat, who could possibly be in the top 3? Well, clearly whoever got first in the first heat could possibly be in the top 3. Anyone wasn't raced yet. So since we've raced 10 in the first heat and 9 new people in the second heat, that leaves 6 racers left in the third heat that are new that could possibly also be there. So they have to race for sure. And then maybe whoever got third place in the first heat, right, they might be able to be third overall too. So they probably, they might have to race. And then, you might be thinking, well, that's 8 people already, right? The first place in the first heat, third place in the third heat, the 6 people that haven't raced yet. And then I've got in addition to that, whoever got top 3 in the third heat probably might be able to be in the top 3 overall too, right? So they have to race as well. So doesn't that make 11 people, and isn't that bad? Well, no. And the reason that that's not true is because I know something about how those top three relate to whoever got third place and potentially even whoever got first place in that first heat, depending on how the results go. So I definitely need to take first place from the first heat, right? There's no way I can eliminate the possibility that first is better than anyone from the second heat because they didn't race it, and they got first in the first heat. I also definitely have to take the 6 who haven't raced, right? So assuming that my answer is correct, what that leaves us with is we only have 3 more racers I can take between whoever got third place in the first heat and whoever got the top 3 in the second heat, right? Because if you got fourth in the second heat, there's no way you're third overall. So it's those 4 racers we need to think about who could possibly win. So I'm going to relabel, I'm going to call whoever got second place in the first heat. I'm just going to call them 2, so I can just say 2 from now on instead of second place in the first heat. And I'm going to call 3 the person who got third place in the first heat. If I say 1, that probably means first place in the first heat. So between 3 and whoever got the top 3 in the second heat, we need to figure out, again, just restating here, figure out which 3 we're going to bring to the final heat. So which of these 4 contenders could possibly be in the top 3? And the answer is, well, it depends. And it depends on how 2 did in the second heat. And in theory, 2 could get anywhere between first and 10th place in this heat. But the only thing we actually need to concern ourselves with is whether or not they won, right? So if they won, then whoever got third place in the second heat cannot so this is not 3. This is third place in the second heat. They can't possibly be in the top 3. And the reason is that they lost to 2 players, right? So if they're third in the second heat, they lost to 2 players, but they also lost to someone who lost to 1, right? First place in the first heat. So that's three races that they are slower than, so they can't possibly be in the top 3. So what we're going to do is take the first 2 racers from the second heat. We're going to take 3, and those 3 plus 1 and the 6 new racers will be the final race. Now, what happens if 2 didn't win? Well, now 3 can't possibly be in the top 3. Why? Because they lost to 2, they lost to 1, and they lost to someone who beat 2 indirectly, right? So it's that transitive property that we talked about earlier. So now what we're going to do is take the top 3 from the second heat, ignore 3, right? Third place from the first heat, and then also add to that first place from the first heat and the 6 new racers. So either way, we only end up with 10 racers, and then whoever are the top 3 from that heat are the top 3 in order. So that's it. Hopefully you figure that out, and we'll move on to the extra credit. Now, in this scenario, we actually have 6 racers, so you might think it's easier, but I can only race 2 at a time, so that's harder. And we want a full ordering, first to 6th, so that's also harder. But this is actually also a well-known issue, right? I mean, this, at least to me, fairly obviously, I don't know how to explain if it's not straightforward, it's not intuitive, but this is basically just saying how many comparisons do I need to do in order to sort a list. And if you've ever taken a computer science course or done anything with sorting, this is a kind of fairly fundamental question in that discipline. And because it's a fundamental question, it's been studied a lot. It turns out there's a particular type of sort called a merge insert sort that at least weakly has the fewest number of comparisons for any number of items in a list less than or equal to 22. And I think it's the fewest number of comparisons known, meaning that it's possible another algorithm could beat it. They haven't proven that doesn't exist, but that no algorithms are known to beat it, up to 46. So I think maybe at 47. I might be getting the number wrong, but it's something like that. That there might be other algorithms that do this better. And now in actual computer science, right, we don't actually compare about only the number of comparisons, right? Because there's kind of this trade-off between the comparison that you do and how much time it takes to resort the list after you do that comparison. And so, well, this is getting outside the realm of the question, but basically, the number of comparisons is not the only thing you care about. But if comparisons are very, very costly relative to, say, sorting a list for some reason, then it could be the primary factor. But anyway, so what does a merge and sort look like? I'm not going to get too much into detail, but the basic idea between a merge, insert, sort is to split your data into pairs and then do a bunch of binary sorts. And this number 6, I think, was very carefully chosen here because it has a very nice binary sort property, which we'll see what I mean in a second. So again, we're gonna split the 6 racers. We're gonna race 1 versus 2, 3 versus 4, and 5 versus 6. And then, we're just gonna relabel that. So that's gonna use 3 of our comparisons. And then we're gonna relabel, we're gonna assume that 2 beats 1, 4 beats 3, 6 beats 5. And if that's not true, just relabel it, right? We call whoever lost the first race 1, call whoever won the first race 2, right? And so on and so forth. So now we've got those 3 comparisons and those 3 orders. And then we're going to want to order the highest of those 2, 4, and 6. You could do this equivalently by ordering the lowers and doing everything from the other side too, but we're just going to do it from the higher side. And how do we order those 3? Well, it's going to take 3 comparisons. I basically have to compare each one to the other 2. So 2 versus 4, 2 versus 6, and 4 versus 6. And again, we're going to assume we get this 6 greater than 4 greater than 2 order, which may not happen, but if it doesn't happen, we'll just relabel everything so that 6 is, 6 is the racer that got fastest between those 3, 4 got middle, and 2 got the slowest time. And then again, because we relabel those, we'll also have to relabel 1, 3, and 5 so that 1 is whoever lost to 2 in the first round, right? 3 is whoever lost to 4, etc. So now we actually know the order we know 2, 4, and 6, but we also know that 2 beat 1. So we know the order of 1, 2, 4, and 6, and we've used up 6 comparisons. And at first glance, this might actually look kind of bad because if I only had 4 elements, I could actually sort them using 5 comparisons, not 6. But I have 2 pieces of information that I wouldn't have if I were just trying to sort the 4, 1, 2, 4, and 6. Namely, I know that 5 is less than 6. I know that 3 is less than 4. And here, now I need to somehow insert 3 and 5 into this list in as few comparisons as possible. And it's really important which I do first here. And I'm going to give you a second maybe to think about why that's true. But it's really important which one I do first. And the reason it's important is this idea of binary sorting. The way it works is basically you take a number and you compare it to the middle of a list, right? And if you compare it to the middle of the list, that divides the list into things that it's bigger than and things that it's less than. And you basically are splitting the list in half. And if there were a big long list, you would then take, well, what's the middle of what's left, right? Compare it against that number. And then that again, we'll compare it, we'll cut it in half. And by cutting the list in half each time, you're minimizing the number of comparisons you have to do in your worst case scenario, right? Because in the worst case scenario, you kind of keep the bigger group. And if the groups are 50-50, then, the biggest group is as small as it possibly can be. This is kind of like the cookie splitting problem where, one child splits the cookie, another one takes the cookie. What does the first child do? They split it exactly in half. So anyway, this is, and the reason it's nice here is, well, if I were to sort 3 right now, I could do, I would potentially have to do 2 comparisons, 1 and 2, right? But if I try to put 5 in the list, I also only need at most 2 comparisons, right? First I compare it against 2, and then against 1 or 4, depending on whether it's bigger or smaller than 2. And because 5 kind of has more places to go, I want to do that comparison first. And it turns out that wherever 5 goes, basically the idea is for putting 3 in here, in the worst case scenario, it's the same number of comparisons to figure out where you go in a list of 2 as to figure out where you go in a list of 3. It's 2 sorts either way. So I'm going to do 5 first, so that 3 still ends up with only 2 more comparisons when it gets to them. So anyway, start with 5. Where does 5 go? It's definitely less than 6, but there's 3 more places it could be. Well, I guess it could be in 4 places, or it could be left of 1 or right of 4, or anywhere in between. So compare 2 versus 5, and then compare if 5 is less than 2, compare it to 1. If 5 is more than 2, compare it to 4. And then I'll know where it goes in the list. Right? So now I know this order. 5 doesn't have to go there. It could go anywhere in this list. And we've used 8 comparisons because we had 6 before. We used 2 more to put 5 in there. Now, what's the worst case scenario for placing 3? Well, I know that 3 is less than 4. So I think the worst case scenario is we're going to assume 5 is also less than 4. Because if 5 is more than 4, it's kind of one fewer number I have to compare it against. So we're going to assume that 5 is less than 4 to make it as hard as possible. And then 3 is somewhere in this list of 1, 2, and 5. It's somewhere either, it could be less than any of them or more than any of them, but it's somewhere in that list. Because it's definitely less than 4. So we're going to ignore the cases where it's more than 4. So just like with 5, we're going to compare 3 to the middle of that list. And I don't know what the middle of that is because I don't know what 5 is, but it doesn't matter, right? If 3 is more than the middle number compared to the high number, if 3 is less than the middle number compared to the low number, and with those two comparisons, we will know where 3 goes in that list. And then you'll put 4 or 6 on the end of it, and that will be the sorted list, and it took 10 comparisons. Now, the only question is, this is a merge insert sort, so in the worst case scenario, this must be, not by any proof I did, but, there's a lot of, computer science papers out there that have shown that this is the fewest comparison sort in with 10 in a list. But can we do better? Could we, in theory, do 9? So, but there's a fairly simple proof that it can't be done in 9. So I'll give you a second to think about it, but I will just go into it right now, which is I'm going to compare how many possible orders there are to how many possible orders you could make with 9 comparisons. So it can't be done in 9. Why? Because how many lists can I order? How many ways can I order 6 numbers? Well, it's 6 factorial, which is 720. Now, how many things can I possibly disentangle with 9 comparisons? Well, each comparison basically disentangles 2 things. And so if I do that 9 times, I could disentangle 2 to the 9 things. But 2 to the 9 is only 512, which is less than 720. So there's no way we could possibly do it in 9 comparisons. So 10 is the least possible. We can do it in 10. So this works. And that is it for the Fiddler. Thanks for watching, and we'll see you again next week. And please let me know if there's anything about this that wasn't clear, or if there's anything you want expanded on in a future video. All right, thanks. Bye.